So this video is about section 17.5 in Halliday, Resnick, and Walker's book. And here we're going to be talking about interference of sound waves. So just like the traveling waves, the transverse waves that we studied in the previous chapter, sound waves are waves, so they're going to interfere. So the particular scenario that we're looking at is if I have two sources of sound waves. So these are my sources, 1 and 2, and then I could be standing at some position. So I'll put this position P. So P is where we're going to listen, or we're going to detect the sound waves. So these sound waves are going to they're going to proceed outward, and basically going to get some interference, this overlap of the sound waves between the two sources. And so instead of writing these wave fronts as these little circles, instead now what I'm going to do is draw out rays. So let me redraw this. Now with the rays instead of the wave fronts. So I've got source 1, and I have source number 2, and I've got our listener out at P, and now I'll draw out the ray. This one is L2, and this one is L1. So the distance between the source 1 and the listener at P, the distance is L1. The distance between the source 2 and the listener is L2. And so the question is, when are we going to get some constructive and destructive interference? So what happens is, if I was to draw a cross-section of those wave fronts, what I would find is that I would have basically a wave that runs along this ray like this. And so to get the interference, what I would have is wave number 1 and wave number 2. And if the to get some constructive or destructive interference, I would have to match these waves. Say they have the same wavelength. I would have to match them to the change in the distances, because what I have is, let me try this another way. If I draw out the length L1 and I draw out the length L2, then the wavelengths should match up with each other like so, such that the change in their wavelength, change in the length, delta x, has to match a wavelength in order for them to get, say, constructive interference. It would have to match up to half a wavelength if I was going to get destructive interference. So I can write this down now mathematically by saying the change in the wavelength it has to be basically some fraction of a total wave, the change in the length, the change in the difference between wave number 1 and wave number 2 has got to match up with a total wavelength lambda, and then the number of wavelengths I get depends on how far out of phase I am. So I could write this then as a fraction of the phase difference with 2 pi radians. Or let me rewrite this. So if I divide both sides by the wavelength, I basically find that the path difference, delta L, matched up to the total wavelength lambda has got to be equal to the phase difference between the two waves. So again, if I write out those waves as S1 is the maximum amplitude times the cosine of kx minus omega t, and S2 is Sm cosine omega x minus kx minus omega t, getting ahead of myself, plus some phase. Basically, that phase over a total of 2 pi radians would have, that fraction should be the same fraction of the difference in length that the waves have to travel over one whole wavelength. So in this case, I would get constructive interference. Basically, if the phase was some multiple of 2 pi. So m is just an integer that goes from 0, 1, 2, dot, dot, dot. So if I have an integer number of wavelengths, then I'm going to be in phase, basically, and I get constructive interference. So if that is the case, then I'll know when I get this interference by measuring the difference in the two paths between the waves, and then multiplying m times lambda. So if I have an integer number of wavelengths out of phase, then I'm going to get constructive interference. Now, if instead what I have is, if I want destructive interference, I would now have to be, 180 degrees out of phase with it. So I can write down that phase as 2m plus 1 times pi. So that's going to give me phases of, so if I go m equals 0, 1, 2, then that's going to give me phases of pi. If m is 1, I get 3 pi. If m is 2, I get 5 pi. I basically get these odd integers, or basically saying I'm always 180 degrees out of phase with the wavelength. So therefore, for destructive interference, the difference in the path length has to be 2m plus 1 times the wavelength, where m is equal to 0, 1, 2. So this is destructive interference. Yes. Okay. So yeah. So then you get that number of wavelengths away. Okay. So then, like I said, once you know exactly how many wavelengths you're out of phase, then oh, I'm sorry. I thought something was wrong. So let me go back. I jumped ahead. Okay. So let's try this again for destructive. So we have the equation that the phase angle has to be 2m plus 1 quantity pi. So I have to be 180 degrees out of phase. And then I go back to my original equation that I have delta L over the wavelength is phi over 2 pi. So the part I missed was the 2 pi. So if I look at my equation up here, I have 1/2 phi over pi. That is the 2m plus 1. So therefore delta L over lambda is 1/2 2m plus 1 times pi. So I could write this as the path length is half a wavelength times these, whoops, don't need a pi there. So I'm one half, half a wavelength times these odd numbers, these odd integers. Or I could bring the 1/2 inside and write this as a wavelength times m plus 1/2. I think I kind of like it better this way because it shows that you always have half a wavelength. So if m is 1, you're half a wavelength out of phase. If m is 2, then you're 3/2 a wavelengths, and then 5/2, 7/2, so forth and so on. So this is the equation you want to use for destructive if I can spell. Destructive interference amongst sound waves. So this is really useful. I mean, this is a useful type of exercise. One, because if you're trying to set up the sound system for a room, you want to know exactly what the lengths are, delta L, and the other parameters like the wavelength of the sound, in order to figure out where are the dead spots in the room that you're not going to hear anything, where you're going to get really good sound, and so you want to actually figure out. I mean, you could figure out where to place like the sources, the speakers. Another one you can think about is like the transmission of sound such that you don't want to wasted space. Where are you going to put your speakers such that you get the sound, say, going forward, and then you have places where it's destructive interference, where you don't want to disturb the environment around it.